Let me throw GM in the chat. GM, GM, GM. So yes, please interact. I'm going to assume that you guys know a little bit about smart contracts and syntax, and you can go get more information. I'm just going to throw some links in the chat at ethereum.org. Um, I'm on tour. I go to a lot of universities and teach this kind of stuff. So here we are. We're already attached and we're at the university, but I don't know if you run a blockchain club and you want us to come visit and do a presentation similar to this, always hit me up. Oh, there was a WETH contract. I want that back. Smart contracts. You guys have already talked smart contracts a lot, but I just wanted to show this off real quick. This is a smart contract. Right here is the code. Let me zoom in on it. It's pretty simple Solidity code that does, whatever it's programmed to do. When you build something in a smart contract, it's going to do exactly what it's programmed to do. No one can tamper with it. No one can take it down. Ethereum has been up for 10 years without a single second of downtime. So when you deploy something to Ethereum, it's always up. You can ask any node in this giant peer-to-peer network values from that network, or you can go to something like Etherscan. This is a block explorer where you can see the code and look up, addresses and their values. But here's some simple code. We can look at this code as programmers and see exactly what's happening here, right? There's some balance storage for some address, and we're incrementing it by whatever the value is that they sent in. It happens to be a payable function, and people can send in money, and then we increment based on the storage of whoever sent the money in. So this deposit and withdraw, these two functions basically accept money and keep track of how much money you've deposited, and then you can withdraw the money back out, and it actually burns a token. It basically takes in money and gives you a token, and then takes in the token and gives you the money back. Very, very simple code. Any programmer can get onto this and see this exact code. But what's really interesting here is the amount of money in this single smart contract. $9.2 billion are locked up in this single smart contract. And this is the WETH contract. It's the wrapped Ether contract. So what you do in this contract is basically take Ether, the native asset on Ethereum, and turn it into WETH, which is an ERC20 token. A lot of times you'll use protocols that want you to swap from token to token instead of from Ether to a token. And so to make everything on the protocol use ERC20s, you sometimes have to wrap up your Ether into WETH. But just wanted to show this simple smart contract to show that little chunk of code has an address on Ethereum just like any other user, and it has $9.2 billion in it. So that's pretty cool stuff. Okay, I'm Austin at the Build Guild. You can find the Build Guild. We have lots of stuff. We do lots of teaching and building and funding. Our main curriculum is Speedrun Ethereum. And if you're a technical developer, let me paste that into the chat, and you're looking to learn more about how to build on Ethereum, this will take you through tokenization, staking apps, building a token that sells in a token like vending machine. It looks at randomness on chain and how to produce randomness, and it actually sets you up so you can attack this randomness and build your own contract that only plays this dice game if it's going to win money. Then a DEX, right? Like once we have tokens and we can send them around, the thing that we want to do is swap those tokens one for another. And a DEX allows you to do that in a fully decentralized way, meaning it never goes down. You can always swap, and no one can tamper with it or steal your money. It all works based on just code. And we get farther, we talk about lending. Lending comes down to this like over collateralization concept where you can't just lend to anybody on the internet value, right? They will just take your money and run away. So what you need is to have over collateralized lending. And what you do is you have them lock up, let's say $200 of collateral, and then they borrow $150 of some other token. And as long as the value of that token is always worth more or always worth less than the collateral that's locked up, you're fine. But if something happens, and they can come back and repay that token and get their collateral back at any time. So the collateral is always still theirs. The token is borrowed and theirs to play with. They can bring back the token and get the collateral out. The thing that happens that's bad is if the collateral ever starts to be worth less money than the token they've borrowed, you have to have a liquidation mechanism in your protocol. And it's not just a liquidation mechanism that you run. And this is an interesting kind of aha moment that you need to have about smart contract apps, is that anyone can run the liquidation. And this is a key concept and mechanic. Anyone can liquidate anyone else if they meet some certain parameters. If you've borrowed $150 and your collateral is all of a sudden worth less than 200, maybe like $160, it needs to get liquidated. And even if the platform ran a whole bunch of computers in a whole bunch of places and they had them checking in, making sure they run the liquidation, it's still not as good as if you allow this liquidation to happen by any account. And in fact, not just by any account, but it's incentivized. There's an incentive there, and whoever runs the liquidation gets paid money. So it allows any third party in the world, anywhere in the world, to basically push the button to liquidate this loan. And when you create a mechanism like this, it guarantees that it's going to run. And so the protocol always stays whole by guaranteeing that if the collateral is ever worth less than what was borrowed, anyone in the world can liquidate it, and they're incentivized to do so. And this is a real aha moment about how you need to build things on a blockchain. You need to provide incentives and allow kind of anyone to poke it to get it to run. We talk about stable coins and what makes stable coins stable, and how there's kind of like these kind of tensions between the rates. You have a rate to borrow and a rate that pays off for locking up the stable coin. Prediction markets are really hot right now. It's basically two tokens. You deploy kind of two meme coins, and you have an oracle that guarantees it will kind of rug one of the meme coins for the other one. So we could say, will this person win the presidential election, yes or no? You can buy the yeses or the nos, and then if that person does win, the money that was in the yes pool goes to the no, or the money that's in the no pool goes to the yes, depending on if they win or not. Cool. There's a question already. How exactly does someone interact with a smart contract? Is that doable through Etherscan? Okay, cool. So when you make a transaction on Ethereum, let's go to eth.build real quick. I have a little, oh, whoops, I don't want to capture that. Oh man, what am I doing here? Sorry. I want to open a new tab. Here we go. Okay. How does someone interact with a contract is the question, right? So first of all, let's talk about how a transaction works, right? And a transaction works using a key pair. Let me go over here where I have a fresh, everyone on Ethereum has what's called an ECDSA key pair. And what that is basically this big private key. If you want to create an account, if you want to create an address on Ethereum where people can send money, you basically just generate this large private key. And you can see here, I'm just generating a private key, and I get an address that's derived from that. And what this private key can do is sign messages. So if we plug that private key in here, and then we have some message, let's just say hello world for now. Okay, now we can sign that, right? I'll just have another button that allows me to sign the message. And so what goes across the internet could be your message and your signature. And you can send this out to anyone. And then on the other side, people can use math, people can use cryptography to plug that message in and that signature in. And what they'll get out is the address that signed that message. And we can see that these two are equal here. So this is like this really key concept to how you interact with blockchains, how you send money on blockchains, how you use cryptographic key pairs. You basically have this private key, and this private key can sign a message, and then later on, someone can cryptographically recover who the address is that signed that message. And this is the basis of all this kind of stuff. So let's say Alice wants to send money to Bob. What she's going to do is she's going to say, I want to send five tokens to Bob, right? And she's going to sign that message. And across the network, everyone sees that Alice wants to send 5 tokens to Bob, and she's signed it. And we can prove that this is Alice's address and she wants to send money to Bob. So we have a whole ledger and there's a consensus process, but basically this is it. This is how you prove that Alice wanted to send money to Bob. So in a very similar sense, instead of I want to send 5 tokens to Bob, you say something like, I want to call the increment function on the counter smart contract, right? And actually there's a to address and everything like that, but this is basically the gist of it is you sign a message that says, I want to call this function with these arguments on this smart contract. And then that gets mined into the blockchain just like a normal transaction does, and the nodes all run that. And that's how you call a function on a smart contract. Just the same way as you send money, but with some extra information about what you want to call and what the arguments are. Great questions. Keep them flowing.
And those things, just to be clear, like, do you really write text and then there is an A, there
No,
is an
no, it's
AI?
like
Yeah, there is
it's
an
an
AI.
object, right?
Okay,
Yeah.
yeah,
You would
yeah,
turn this into an object and there would be a to, and there's some address there,
yeah,
and
yeah.
there's a
Okay,
data field is what it is. And that data field is just some hexadecimal numbers, and it's
yeah,
basically all of this information encoded
right,
into that data
right.
field.
Do
Yep.
you have an AI agent who is doing this already, where you specify text and then it translates it into this?
Oh, you can just do encoding probably. I probably have a utility here to do the encoding. RLP encoding is
Uh,
maybe what it's called, something like
okay,
that. Yeah. Okay.
yeah.
Whoops, I didn't mean to close that. Let's bring that back up because we might need that later. Okay, next question is when do you use public versus private key? Okay, so uh, the public key, let's go back to that. The public key you can share with anyone. You basically give everyone your public, and it's not really the public key. There's actually a private key and a public key. And then what we're doing is we're like hashing the public key, and we're taking the last like 40 characters of that public key, 54EA, and that's what we call the address. But in terms of public and private, think of your address as your public identity, and your private key you do not want to share with anyone. This is really important because this private key, let me get rid of this private key right here is super important. Basically, if you lose this, your money is gone forever. If you leak this, someone is going to take it and send themselves all your money out of your account. So if you lose this or leak this, your money is gone forever. You have to keep this very, very secure and safe. And what's interesting is we could sit here and generate private keys all day long, and we'll never find an account that has money on it. There's enough entropy, there's enough digits in this giant hex string that you can basically generate them as fast as you can with all the compute power in the world, and you're never going to find one without or with money in it at the current compute power of the world. All of that will change with quantum computing and other things like that. And Ethereum is working toward being quantum safe in the next 5 years. But with the current CPU power, we can sit here and generate private keys forever, and we'll never find one that has any money on it. Okay, so hopefully that answers that. Private key stays private. You use the private key to sign messages. Public address is what you tell everyone, and people send money to your public address. So it is just string encryption, or is the encryption some other data point? I don't know if I can answer that question. It's ECDSA key pairs, so it's doing an ECDSA signature. It's not exactly encryption. You can do this. You can encrypt a message also, right? I can take your public key, right? I can take your public key and I can encrypt some message. This is a secret, right? And I can send that across the network, some giant object that's encrypted. I don't even know what we do with this. And then you can use your private key to decrypt it. So it's not message encryption, it's message signing, okay? But let's see, we could take this encrypted data and we could take your private key and we could get the secret out of it, but only the private key can get this information. So you can know someone's public address and you can write a message to them and you can encrypt the message with their private address. And it just looks like this when it goes across the wire. And only the person that has the private key can decrypt it. So it's a little bit different than encryption and decryption. It's actually sign. So you're using the private key to sign a message, and then anyone in the world using that message and the signature can recover who signed that message. So it's message signing, not message encrypting. Hopefully that answers that question. Okay, let's keep going. We got a lot to cover here.
Yeah,
Hopefully that answers it. But please get the questions in the chat. If you're
yeah,
confused about something, let's put it in there. We talked about sending value from one person to another. And we talked about calling functions on a smart contract, but there's one other kind of transaction we haven't talked about, and that's deploying a smart contract. And basically what you do is you just don't have a to address. You sign a transaction with no to address. It's just data. And basically what that data is the smart contract encoded into hex. So if you see a transaction with no to address, that means I've got this data and I want to deploy the smart contract to Ethereum and I want it to live at a new address. And what will happen is an address will be derived from all of this, and this contract will land at that address, and then anybody else can call functions on that smart contract. So those are kind of the three kind of different transactions you might make. Hopefully that also fills in some extra information here. Okay, so we've talked about Speedrun Ethereum. I pasted it into the chat. You as developers should just go through Speedrun Ethereum. It's going to give you the tooling and the information of just like how you go about building things. And that key moment when we were talking about lending there, where you can't just lend money to people on the internet because you can't trust them. What you need is a mechanism of over-collateralized lending that allows the platform to always stay whole, as long as you have a nice liquidation mechanism that keeps the loans from going under collateralized. Stable coins, prediction markets, zero knowledge. Real quick, we should just hint at zero knowledge. I know this is an agentic class that we're talking blockchain in, but also another really cool tech here, along with AI and blockchain, is zero knowledge. Go learn zero knowledge proofs. Go learn how you can use math to prove something without leaking any information about it, and then someone else can use math to verify it. Just like we had that sign and recover box, you can imagine a prove and verify box where you put some information into the prover. It gives you some receipt. You take that receipt and put it in the verifier, and the verifier verifies that yes, this certain thing is true without having to give the information. Always the fun example is if you want to get into a bar, you have to prove that you're 21. But when the bouncer sees your ID, he can see like where you live and a lot of extra information about you that you don't want him to have. A ZK proof system would let you put your ID into a box and it generates a proof that you are 21. And then you take that proof to the bouncer and he puts it in another box and it gives a little green light that says, sure enough, this person is 21. You don't have to see their ID and all their information. So it allows you to prove things without giving up any information. Okay, so when you deploy a contract, it's actually compiled hex that gets saved to the new address. So the solidity, exactly. The solidity is compiled down to something that looks like machine code. You can actually write assembly code and that still gets compiled down to machine code. So you've got solidity, and I think even solidity may go to like a subsequent language like UL, and then that goes to machine code. But you can put assembly inline in your solidity, but yes, all of that gets compiled down to machine code, and it's machine code that lives on the blockchain. Shoot, I keep closing things. If we go back to that WETH contract, they give us the code here, and we can see the code here. But when you first deploy, it actually looks like this. This is the contract. This is the deployed bytecode. So this is the bytecode for that smart contract. Right. So all of this is basically that contract in machine code. And you can go learn about all the opcodes and the cost. Like there's a gas cost for each opcode. Gas is a whole nother worm we can get in, or rabbit hole we can go down. The TLDR, I guess we should cover it real quick. I think probably you guys covered it in the class, but maybe I should talk about it real quick, because there's blocks, right? The chain is full of these blocks. These blocks are getting produced every 12 seconds or 13 seconds. And within that block, you can only fit so much data. If we go look at Etherscan, we can see the blocks going by here. Within each block, so here's a block, there's only 248 transactions, or 109, or 205. That's basically the limit of the execution you can do within that block. And so what the miners are doing is taking all of the possible transactions in the mempool, loading them up in a block, in the most greedy way possible so they make the most money on gas. But if you imagine there's just a limit on block space, and so when you're trying to get your transaction in, you pay some gas. And this is basically a bribe to get into that block. It's like a bid, it's like an auction. And so the miners are always picking the highest bid transactions and putting them into the block so they make the most money. So when there's congestion and lots of people are using Ethereum, you have to bid higher. You have to pay more gas to get your transaction to land, but it's all like an auction process that happens. Hopefully that's a good TLDR of gas. Okay. Now we're talking agents and we're talking Scaffold-ETH. Eventually, we're going to go build an app, but I want to save that to the end. We'll build a smart contract app, but I want to cover some more concepts first. Usually what I do in my presentation is I go start building an app right now, but I think we may not have as much time as I usually do. So I want to kind of like make sure we cover all the concepts and we get all of our questions out. And then at the end, I will show you how to build an app. Basically, we'll deploy a smart contract. We'll deploy a front end that talks to that smart contract. And I probably won't even write a lot of code. I will probably use Claude to help me write both the smart contract and the front end. But let's move on to interesting agentic things that are happening that are sort of blockchain adjacent, and then we can go from there. So the first one is EIP8004. And this is trustless agents. Let me drop it into the chat. And these dudes, you had said something like Austin was the AI guy at EF. This guy right here is the AI guy. Davide at Ethereum.org is the man. He knows. And I think, did we ask him to maybe submit a video or something?
I think I asked him to create a small video. He has not responded yet. I know Davide, he was a Columbia student in the business school.
Oh, he was amazing. See,
Yeah.
you've got him. You know him. Yeah, that's great. He's incredibly smart, and he's working on this new trustless agents EIP. Or ERC. And what this is basically a standard.
Can you put it on the chat?
Yep.
And Austin, can you put the link on the chat?
It's in the chat. Yep, it should be in the chat now. Yep. I'll try to drop these into the chat as I go.
Okay, I don't see it on the chat.
Also ETH.build. I didn't. Oh no, I'm sending a direct message to someone. Oh no.
Okay.
Yeah. Oh, I see. People were sending me direct messages and I responded.
Let's send message
public.
on the
public,
exactly.
For sure.
Yeah, so that everybody can see.
Okay. Here is that in the
great.
chat. Let me make sure none of my other responses were private. Yeah, please just drop your messages public. You're going to trick me into sending private messages. That wasn't. And ETH.build was the other one. That's that tool I was using there. And it has, it doesn't even turn into a link. How do we make that turn into a link? Yes, please ask questions. Let's answer them. Whatever you need to know, whatever you feel like you're missing in this, let's talk about it. There's a deep well of knowledge around protocol and consensus, but I spend a lot of my time at a layer up, and that's building smart contracts and smart contract applications on top of Ethereum. I run a node, I run a validator that creates blocks. I stake 32 ETH to create blocks on Ethereum. So there's the whole protocol level and the consensus mechanism. But a lot of what we're talking about here is like what kinds of things you build on top of Ethereum, what kinds of things you use Ethereum to build. And hopefully after we look through that speed run, it's kind of clear that you're building these kind of like massive multiplayer games for people to coordinate that don't trust each other. Imagine building a co-op for pirates. That's kind of the thing that you build with Ethereum, where at global internet scale, you can't really trust anyone. You need a trust layer, and Ethereum is that trust layer. It's basically code that gets deployed. Everyone can see the code. The code runs exactly like it's supposed to, or it runs exactly as it's programmed, and no one can change it, and it's always on, right? No one can stop you from getting to it. No one can tweak the code. The code is always there, and it runs and does exactly what it's supposed to do. Okay, let's get on to agents, but feel free to drop more questions in the chat as we go. What would we use Ethereum for in the agentic world? We see AI agents popping up everywhere. We're realizing that pretty soon, maybe this is debatable, but pretty soon my computer sitting here is going to be smarter than I am. There's going to be agents doing lots of tasks all over. We'll probably all have, maybe AI will be the new UI, and instead of going to Google and doing something, I'll just talk to my agent and it will go do things for me. you guys know more about agents than I do, but what would we use Ethereum for in the agent, landscape? And what that ends up being is kind of like a registry. I don't know, like phone book may not be the right analogy because you're all a lot younger than I am, but you could go to a new town and you could open up a phone book and you could find someone's name and you could call them on the phone. That's sort of what's happening here. If that phone book also had reputation and you could see like, oh, this guy is a plumber and he has 4 out of 5 stars. So maybe we're thinking more of like a website that's like Yelp reviews, right? That's kind of what this registry aims to be. It's basically a registry where you can discover and find new agents. And there's a reputation for each one of those agents and what they can do. So you learn about the agents, you learn what their abilities are, and then you can see some kind of like valid reputation for how well they did that thing. So you can imagine some agent whose job it is to write a poem. Or let's say it's writing copy. This agent writes copy. We know lots of agents that are really good at writing copy. There's another agent who's really good at generating images, right? And there's basically what you want to be able to do is discover, let's say we want to run a marketing campaign and we want to run 100 different ads, 1,000 different ads over the course of the week, and we want to see which ones do the best. And so what we'll do is we'll tell an agent, hey, go run 1,000 things, go. And that agent will then go talk to these other agents. It will look up, well, I'm going to need someone to write copy for me. I'm going to need someone to generate images for me. So it finds these agents. It's going to look at which one has the best reputation. And it's going to say, okay, this agent has a good reputation for creating text. Start creating me text about whatever the thing is we're advertising. And then he'll go to the image one and say, hey, you generate me images. And it will start generating a bunch of images for them. And then if they're good, they can actually like give a thumbs up on their reputation. So that's what ERC8004 is all about. It's allowing agents to discover each other and also have some kind of reputation validation where you can verify how many stars this person has or how many other agents have given a thumbs up, or how many times has this agent done its job correctly. And we can get in here and see all this stuff, but it's basically just a standard. It's just a registry standard system where there's fields and feedback. I guess this is feedback file structure, but it's what can the agent do and how well has it done it in the past is kind of what you're getting from this registry. Okay.
Right. And
let's see.
who's doing the thumbs up, Austin, with me? If an agent does a good job, then the other agent that has interacted with it will put a thumbs up, right? It's
Yes,
more like
I think that is it.
it's based on bilateral interaction, right? Or any other agents can also put a thumbs up. We can see that this agent is working well with other agents, and they can say, okay, this agent deserves credit.
Yes, I think so. And even the agent that's thumbs upping needs to have their own reputation too, right? Or you could just Sybil attack this and spin up 1,000 agents and have them all thumbs up you. So there's got to be like the thumbs up has to have some value based on how often that other person has given feedback. I don't know exactly how this all works. Davide would be able to answer that better, but there's some kind of reputation system, and even the person giving the thumbs up has to probably have some kind of reputation, or you could just Sybil attack it by creating a bunch of accounts and thumbs upping, right?
Yeah.
Okay, cool. Ask questions if you have them. That's the most I know about this, but if you get in and you look up 8004, Marco is always doing Twitter spaces. He's always doing lots of stuff. You can find out tons of information about that.
There are a couple of questions, Austin, on the chat.
Yep, here I go.
Yeah,
okay, so what if you deploy a smart contract and later discover a bug in the code? How do you invalidate the old contract? Okay, so this is a really interesting thing. Basically, you can't. Like the short answer is once you deploy a contract, it's there forever. You used to be able to like destroy a contract and people were like, wait, we don't want that. And they basically completely took it out. You could program in some kind of upgrade system. You can actually do this thing where a contract is deployed and it delegates all its execution to another contract. And so this address stays the same, but you can actually like swap out the code. But this kind of goes against the ethos of immutable smart contracts in the first place. So you have to be very careful about upgradable contracts. People do it, and the upgrade system is usually locked down to like a multi-sig, and you have to have like 5 out of 10 people from the company sign this transaction, and then it upgrades the contract. But really, a good smart contract can't be upgraded. You deploy it, and it does exactly what it needs to do. We saw that WETH contract earlier. If there was a bug discovered in the WETH contract, first of all, that $9.2 billion would get stolen, right? But what we would do is we would deploy another WETH contract and everyone would just start using the new WETH contract. That's usually what happens. I think WETH is actually named WETH 9. I don't know if that means there were 9 iterations on the WETH contract before they got to that one. It's such a simple contract, I doubt it, but the way you usually migrate is or upgrade is you create V2 of your platform and everyone starts using V2. And then if you want to add new things, you create V3. And V2, if it's deployed correctly, always stays up and does exactly what it's supposed to do. And then V3 has these new features. And if it's good, people just might kind of migrate. So there is no like forced upgrades. You know how that works. If there's a fun game or application you're playing, if the developers want to, they can rug the app and they can upgrade it and they can add new features and totally destroy all the old stuff. And you as the player are completely at their mercy. On blockchain, it doesn't really work that way. Basically, the app is deployed forever if it's deployed the right way, and you can't change it and you can't take it down. Not even the person who deployed it can take it down. Okay, next question. How would this enable less frequently used, but practically speaking, still well-performing agents to be chosen by other agents to be used? Yes, I think the registry is going to have some kind of reputation system. And you could say, and it's probably going to say like this person has done the job right 5 times, and this person has done the job right 5,000 times. But maybe like this guy has all 5 stars and this guy has some 2 stars. I don't know exactly how that looks, but I think that they will build that into the system. I don't know enough about the details to be able to answer that though. I think pay attention to this standard and see how it's implemented, and you can probably answer that question better than I can. But I'm assuming there's like a reputation and a frequency that is built into this, and there's some kind of like this guy has, 5,000 ratings and this many stars, and this guy has this many ratings and this many stars. Okay, can you explain what you were saying about how gas is used within Ethereum? Yeah, gas is a whole thing, but the TLDR is that gas is your bid on block space. Each block is mined every 12 to 15 seconds on Ethereum, and there's only so many transactions you can fit in that block. There's only so much execution you can do per block. So there's all these transactions that want to get executed. When you decide you want to put something on chain, you go sign it, right? We saw that in eth.build. You sign some message and then you put this signed data on into the mempool. You basically broadcast it, and all the nodes rebroadcast it. And there's this giant mempool of all these transactions that want to get mined into the blockchain. And basically what happens is every 12 to 15 seconds when that block gets mined, the miners pick out the transactions in the mempool that will make them the most money, and they put them into the block. And what I mean by make them the most money is everyone in the mempool is bidding. They're adding some extra value. So Alice wants to send $5 to Bob, but she'll also pay an extra 25 cents to whoever mines this transaction. See that? So Alice sends money to Bob, but also has to basically pay her bid, pay the gas to get her transaction on chain. And the miners will take the transactions that pay them the most and put them into the chain. So if there's lots of transactions and lots of people are trying to get a transaction in on chain, if the market's moving quickly and everyone's trying to quickly get a transaction in, that bid goes up. All of a sudden, if Alice wants to send $5 to Bob right now, Alice has to pay $5 also. So she pays $5 in gas to send $5 to Bob because the network is so congested. But that's how it's always on, and that's how you do basically like allowing anyone to make a transaction at any time, is there's this bidding system for the block space. You can learn way more about it if you go to eth.build and you go to transactions and you even look at blockchain. We're going to really talk through all of this stuff. So I would recommend just going to eth.build and kind of go learn these more if you want to learn more about gas and blockchain and the consensus mechanism and all of those things there. Are there certifications for dApps to ensure that smart contracts do what they claim to do? That's a great question. Okay. So not exactly. Like basically the code gets posted, right? When we looked for that WETH contract, there's no like certification on here. Like it doesn't say anywhere here that it was audited by so and so, but it probably was audited by so and so. There's auditing firms that can go look at all this code and put their stamp on it and charge you $500,000 for that. And a lot of protocols before they deploy will go to an auditing firm and they'll audit the code and say this code is good. But even then, hacks still happen. People still figure out how to hack smart contracts because you did something wrong. If you go to Solidity, whoops, that's not what I want. Solidity by example, they list all the hacks. And I would recommend this. Let me paste this into the chat. Solidity by example is a great place to first see the syntax, but I think you've kind of been exposed to that already. You can see kind of different applications, but hacks are really important. So there's this hack called reentrancy where you it's weird. You write the code in the wrong way. So basically what you do is in your smart contract, let's say we're sending money to someone, but we're keeping track of their balance. Okay, if what you want to do in the real world is you want to subtract from their balance first, and then you want to send the money to them. But if your smart contract sends the money to them and then subtracts the balance, there's a way that they can have that smart contract catch that and then re-execute back in. They re-enter into the contract before it gets to that next line. If you can think of like recursion, right? A whole bunch of execution happens and then it kind of unrolls and you execute whatever's down below that, right? So basically you re-enter into the contract before it has subtracted your balance and you do the same thing again and it sends you more money. And basically you can drain all the money out of this contract using this reentrancy bug. So you as the smart contract developer know that you need to first do all of your checks and effects before you do any sends. You have to say, okay, Bob is withdrawing $5, so we're going to subtract $5 from Bob's balance, and then we're going to send Bob that $5. So then even if he re-enters, it's going to say, you know, your balance is already updated to not having the $5, so you can't get more money. But go check out all of the reentrancy and other hacks. But yes, no, there are sort of certifications. Basically, there are audits, and there are auditing firms that look at smart contracts and give you the stamp. But I'll tell you what, the best certification that this WETH contract is secure is this number right here. This right here. $9.3 billion. Like if anyone in the world, and they have access to this at all times, once you deploy a smart contract, it's basically out there forever for everyone to attack. So this has been deployed for many, many, many years, and it has $9.2 billion in it, and no one has figured out how to get the money out of it yet. So I would say that like this is the best stamp of approval, the sort of like Lindy effect of a smart contract. How long has it been out there? How many people have used it? How much money does it have in it? TVL, total value log. And you can tell from that. Now, obviously, there are protocols with millions of dollars in them that get hacked and steal the millions of dollars. So that wasn't a great metric. And they had 3 audits, and even those audits missed something. So there's always the possibility that something can happen. But the longer that it's out there and the more people use it, the more people that see it and look through this code and poke at it as much as they can and do everything they can to see if they can get the money out of there and the money stays, the longer you know that it's more and more secure. Okay, hopefully that answers that. We've talked about ERC8004. It's basically a registry for agents. The other interesting thing is this like agent to agent economics. And specifically, oh, and MCP servers. I think you know about MCP servers. We'll get into that in a little bit. Really nice when you can have an MCP server that is aiding your development. But this is a Block Scout MCP server. So basically what you can do is connect this to your Claude and Cursor or whatever other AI you're using, and it will be able to go out to the blockchain and get information about it. Specifically, I was just writing some AI agents that do some value transfer, but we'll get to in just a second. And I was debugging it because it wasn't working. And it was able to use this, and it was able to go out to the actual blockchain and look at the transaction, get the transaction information, figure out what was going wrong with the transaction, and then come back and debug and fix my code. It was really, really cool. It was like full loop, go talk to the blockchain, come back and fix the code. So you can do that with this MCP server. I've pasted in here. Lots of good MCP servers. This is the next thing I want to talk about is you know, error codes, right? There's a 404 error. You've gone to a website before and gotten a 402 404 error before, or a 400 error, but you've probably never received 402. This was sort of reserved for future use. They always wanted this to exist as part of the web, but they just never figured out how to do it. A lot of people tried but couldn't. But I think we've got it figured out. And there's this x402 standard that basically does this. You can imagine you want to go to a website and you make a request, whether it's you as a human or it's a client or a script or an agent. They make an HTTP request and they get back a 402 error that says payment required. Basically, if you want to get the information that's behind this query that you're asking for, you've got to pay some money. And so what they do is this 402 basically returns an error and it says, no, you need to pay. Here's an address and here's an amount. And maybe there's like some extra meta information there. But basically, it's like, if you want to get this response from this request, you need to put some money in. And so what you do is you sign a transaction and you put that into the header of the request and you send it along. And then on the other side, the server receives that. It takes your transaction, it runs it through a validator that validates that this has actually happened and the money has been sent. Actually, there's a what's it called? What is this thing called? There is a thing called a, I was just writing this code. It's called the facilitator, okay? There's a facilitator. So there's a client and a server, and I guess we can just jump into it. There's a server here, and I have a client here, and the client wants to buy something from the server, and the way it happens is the client makes a request to the server says 402 error, the client signs a transaction, sends it back to the server takes the transaction and puts it in a facilitator, the facilitator pays the gas, executes the transaction, and sends the value back to the server that says this is good, they have paid. And so I have a demo of that all here that I just vibe coded up. I don't even have the code like in a repo yet or anything. Basically what I did is I used this code from Natter. Here, I'll paste the code in. Really, really cool dude in the Ethereum space. But this is kind of what you're hoping to have, right? This kind of like, you have some middleware that says my address and some amount that I need to get paid. And then, you know, it's all handled by servers and clients. This is a really nice like look at it. But I think if we get into the actual server and client implementation, it's a little bit more complicated. But here's that code. So starting with this code, basically I've just forked this code down. I opened it up with Claude, with Cursor with Claude. And I said, okay, you know, examine all of his code. And then what we're going to do is we're going to build a service. And that service, this is very blockchain native here. We're making vanity addresses. So let me go back. What the heck is a vanity address? Sorry, there's so many concepts getting thrown at you so fast. But when we generate this key pair, we get this private key, right? And that's derived to an address. So what I'm trying to do here is I'm trying to find one with maybe like some words here, like dead, like DEAD, you could find, right? It's all hexadecimal, right? But what I'm doing is I'm generating accounts trying to find one that has like some kind of interesting word, like leet code or something, right? These are just vanity addresses. But let's say I want to find one with a leading 0. This is how proof of work works. If you go back to the blockchain on Bitcoin blockchain days, The way you would mine a block is you would take all those transactions from the mempool, and then you'd have a little nonce, and you would increment that, hoping to find a hash of the whole thing that has leading zeros. And so what we're doing here is proof of work. There we go. Okay, I found an address with a leading zero. Let's say that's what we're going for here. What I'm doing here with this service is I'm letting you generate Ethereum accounts with leading zeros. So this is some work, right? There's some work that has to go into this because you have to jam and you have to create a bunch of addresses. And so what I'm doing is if you want 2 leading zeros, you can pay a penny, 3 leading zeros, you can pay 10 cents, 4 leading zeros, $1, right? So basically, if you want a vanity address that has lots of zeros, you have to go to this service, right? So let's imagine that there is an agent that wants to use a vanity address to do something else, like on the next step. Maybe there's a service that requires that you have an address with 4 leading zeros to be able to use the service. I don't know why in the heck that would exist, but let's imagine that an agent needs to have these leading zeros to be able to interact with this next thing. So the first thing he does is he goes to the 8004 contract and he says, hey, I'm looking to generate some zeros. I'll generate an account with some zeros in it. Are there any agents out there that can do this? And then some agent has registered there and says, hey, I can generate vanity addresses for you. So then he goes and he looks at the reputation and he makes sure this person is good. And so now what he does is he gets the information for that agent and he goes to talk to him. So what I have here, let me just kill it all and get it back started up. So this is, right? And this server will accept requests. And if you make a request to this server, so let's say we wanted 3 and I hit generate address, I get some error back, right? Basically the error I'm getting is I want this product, 3 leading zeros. And basically I just got a 402. If we were to look at the network, we will see that I'm getting a 402 error. Basically it's telling me you got to pay USDC on base mainnet to this address. And if you pay money to this address, we'll generate this product for you. But I can't owe the money to this address. Basically, what I have to do is create a transaction that sends money to this address and sign it and send it along with my next request. So instead of doing this from the web, I'm going to do this from a client script. So now I've written a client over here. So there's kind of like 3 identities here. So here's our client. This is just a Punk wallet with this client here. So you can imagine there's this client that wants to generate these leading zeros. And then I have, this is the server. Let's see. Nope, this is the facilitator. Sorry, facilitator we'll get to in a second. This is the server. The server is just going to receive money. The server is just an address that will receive some base USDC. So this is a stable coin on the base blockchain. So this server is basically kind of backed by this address. And this client is sort of backed by this address. And this client is going to spend USDC. So we have 49 cents of USDC. The client is going to make a request for 2 leading zeros, which is going to cost us a penny, and they're going to negotiate all of that. But let's see how this does. Okay, and then the third actor here is this facilitator. Basically, I have a third account that facilitates the transaction and sends it back to the server, and I have $25 there. So there's the gas fee that has to be paid in ETH, and that will be paid by the facilitator. There's the USD fee. This is USDC, this is ETH, right? The USDC fee that will be paid to the server. So if we do this all right, the client will pay a penny to the server. The server will generate the client will pay a penny to the server by signing a message, sending it to the server, and then the server sends it to the facilitator. The facilitator pays the gas, puts the transaction on chain. This guy receives his penny. He generates the address and sends it back to the client. Kind of a weird thing there, but hopefully that sort of makes sense. So the server, here is the client. Let's run this. It worked one time before this call. I was just vibe coding it just now. Let's see if this actually happens. It looks like it is working. Sending transaction, settling payment, transferring value. There we go. Okay, so the client just got this back, okay? Here's this address. It's got 2 leading zeros, right? So here's the private key. Basically, we just paid 1 penny for the server to generate this private key for us. Let's see if it actually works. Let's take this. So now we're going to put this private key in here. And look at that. We get an address with leading zeros, right? So it just did the work for us to find this private key that has leading zeros. Okay. And we paid a penny for it. It took, 1.46 seconds to generate. And this guy hopefully received, it doesn't look like he received his USDC. I wonder if that's a rounding error or something. That should say 2 cents, right? And this guy should say 48 cents. Weird. It doesn't, oh, there's the 2 cents. Okay, I just needed to reload. Sorry. And this should say 48 cents now. I guess my RPC server is a little slow. There we go. There we go. So the client paid 1 penny. The facilitator paid the gas. And let's go look at the facilitator's transactions, right? We can go look at the blockchain here and we can see the transactions that this guy has made. And what we'll see is 1 minute ago, this transaction happened. And basically it did this function where it talked to the USDC smart contract and it called some function called transfer with authorization, right? So the facilitator put a transaction on chain that used a signed message from the client to send money from the client to the server. And the facilitator is able to verify that with this transaction, make sure it gets mined, make sure the money transfers. There's the penny that goes from the client to the server, and then send an HTTP request back to the server that says, hey, this dude paid. And then the server can then run whatever the work is. Maybe it's generating copy, maybe it's generating an image, maybe it's like rebalancing your portfolio. Who knows what this can do? And then it sends the final result back to the client. Whoo, okay, so that's that. And you can basically vibe code this. I vibe coded this in 30 minutes. Like I took that repo from Natter that we were just showing here, and I said, go learn all this stuff. And then it came back to me and said, okay, I've learned it, kind of like Neo in the Matrix. I know Kung Fu. So he learned all of this stuff, he or she, it's an agent. It learned all of this stuff. And then I said, all right, now build me a server that generates Ethereum vanity addresses. Now build me a client that calls that server and pays money. And all of us have these Ethereum addresses in, these Ethereum addresses we see here are in like environment files. So I'm not putting private keys directly in my code. And I loaded them up, right? I put some USDC into my client address. Oh man, where is it? It's hidden back here somewhere. I've dropped it. There we go. I put some USDC in this guy, and this guy doesn't even need gas, which is really cool. The client only needs to have the USDC, and it's actually the facilitator that's paying the gas and moving the money, and then the server earns the money. So I could just set up a server that generates these vanity addresses, and money will just start flowing into this account as people are using my service. But again, it's like, how do people discover these services? That's what we're using blockchain for. We're using blockchain as a registry for all of these services with a reputation layer built into it. And then we're using blockchain to actually like move the value, but you don't necessarily need to. Like maybe you're using Stripe or something like that, and they have their own payment processors. This is completely agnostic to chain or token. But in this case, we're on the base blockchain using the USDC token. Woo! And you can too by just forking it. Okay, how much time do we have left? Do I have enough time
You
to
still
build
have
a smart
20
contract
minutes.
app?
20 minutes.
Great.
Yes.
20
And
minutes is enough.
this has not yet covered the AI agent, right, Austin? You're going
Exactly.
to
We have not written any smart contracts yet.
Yeah.
Yep. All of this code that I wrote here is simply a Node.js server and a Node.js client and a facilitator script are the kind of the 3 things there. And I just vibe coded all of these and then sent money through them, and the payments happened on the chain, but there's no smart contracts here. Okay. So BankerBot, we were showing this off. There are AI agents out there that do interact with crypto for you. You could say something like, go buy me, go invest in X, right? And it will go invest in X. Some of these exist already. Alchemy is what I'm using. Whoops, I kind of leaked a key there. Hopefully I didn't leak all of it. Alchemy is what I use for my RPC, speedrun Ethereum, reentrancy, wrapped ETH. Okay, we're ready. We are ready to go build an app. I think I've covered all of the topics. Okay, real quick, why blockchain? Like, why do we need blockchain? And I can answer it really quickly. So this is a vibe check for all of you out there. You can just scan this QR code. If you open up your phone and point it at this QR code, it's going to give you this vibe check website. This is something else that I just vibe coded. It's basically a vote. We're holding a vote. I can see some people connecting here. I'm holding a vote. Basically, imagine if I wanted to be elected president, I would say, let's do a vibe check and see if I'm doing a good job as the president, right? Go ahead and vote. We've got 2 good vibes already. Let me make that a little bigger. Here's the QR code real quick. Shoot that with your phone and get in. We've got 7 people to join. Get in and let me know how the vibes are. How are we doing? How are we doing? Are the vibes good? And it's all good vibes. Now there's a reason for that. Let's let everybody vote here. Okay, we got 8 good vibes. Okay, so it's all good vibes. Now, if we have enough people, someone is going to at least be a bad vibe voter. Here's what I vibe coded this real quick, and I said, build me a voting app that asks how's the vibe. They can vote good or bad. But if you vote bad, it actually gives you some error. Technical difficulties, our servers are allergic. Cosmic interference, okay? This is censorship. When we talk about censorship resistance of blockchain and smart contracts, it's kind of hard to understand. You can imagine if I was on YouTube and I had my account and I had everything there and someone deplatformed me and I got kicked off, that would be a bummer. If I tried to post a video of something crazy and the platform decided to take it down. This is censorship. If I'm coming from a different country and they don't want that country to view this video, they could block them. This all happens with a centralized system. There is censorship. And so what you get is you don't get the truth, right? You aren't getting a true vote here for how the vibes actually are. You're getting a fake vote, right? So this is censorship. And so censorship is bad, okay? Like we don't want censorship. And with decentralization, you get censorship resistance where anyone can get to it. No one can tamper with it. No one can block you. No one can take you down. That's a really valuable thing from the standpoint of access. But also something else can happen here, right? I have the server and I'm SSH'd into the server. What if I just like PM to stop the server, right? Or let's say the server just falls over, right? Now you can't get to the thing anymore. It's dead, right? So this is the other reason why decentralization is really nice is it never goes down, right? I can't accidentally fat finger the service and clear the votes or anything like that. It can't be flooded requests, right? Everyone accessing it all at once and the server goes down. That doesn't happen on Ethereum. When you deploy a smart contract, it's always up. Everyone can always read from it by accessing any peer-to-peer node on the network. And then you can write a transaction through this like bidding system where you pay gas to get your transaction to go through. So anyone in the world could read the votes by just asking any peer on the network, what's the vote count? And anyone can vote by paying a little bit of money and sending it to any of these nodes, and it goes to the mempool and then gets mined into a transaction. So this is my kind of like very, very silly why blockchain, why decentralization example. Now let's get into actually building an app. So I'm going to use, let's see, do I have a Scaffold-ETH? Let me bring this back up and we'll go to Scaffold-ETH. So we're going to use Scaffold-ETH real quick, and we're going to show you how to tinker with a smart contract and build your own smart contract app. So let me paste Scaffold-ETH into the chat. Okay, so I've already run this npx create ETH command. Basically, I ran that right here. Example talking about agents. I ran npx create ETH latest, and I created this folder, and it took like maybe 30 seconds to install. I could do it again real quick. We have plenty of time, but I just happen to have it done. And so we're going to cd in, and you need to run a few things here. We need to first run our own blockchain. This is really cool. So you have your own local blockchain running, and it does everything that Ethereum does. It mines blocks, you can send money, you can deploy contracts, you can interact with contracts. It even gives you all these accounts and all these private keys. Here's a big private key that has, millions and millions of dollars in it. So you have this nice local blockchain that allows you to make transactions on. And then you also have a front end. Whoop, come back here. You have a front end where you can interact with your app, right? And your app is going to get out of here. Your app is going to basically auto-detect changes to a smart contract. So we've got our own blockchain and we have an app, and we're going to deploy a smart contract to our blockchain, and then we're going to interface with our smart contract from our application. And this is kind of a full stack Ethereum build where you have a smart contract and a front end, and Scaffold-ETH builds this nice debug page that we'll see here in a second, right here. And it lets you, it auto generates this debug page depending on whatever you have in your smart contract. So I'm going to open up Cursor and we're going to go look at our smart contract. So this is the stock smart contract that comes out of the box with Scaffold-ETH. We'll go packages. I chose Hardhat, but Foundry is another option. Hardhat and Foundry are great tools. Foundry is actually the app that the most cracked developers use. Most of the best devs are using Foundry. I happen to randomly select Hardhat here. Hardhat is still great. All of it works the same with Scaffold-ETH. You do a yarn deploy, whether it's Hardhat or Foundry, it's going to deploy it. But just like putting that little note there that if you're a cracked developer and you want to write your tests in Solidity and you want it to run fast in Rust, you're probably going to use Foundry, not Hardhat, but it all is going to work the same here. So here is our smart contract. It's a simple smart contract that basically is a greeter smart contract, a classic greeter, which means you can send a string in. It keeps track of some greeting. Where is it? Right here. Building unstoppable apps. That's the greeting, right? We have some string that's public that we keep track of. You guys know the syntax of Solidity. You've already kind of learned some of that stuff. If not, go to Solidity by example.
I covered some of it in class.
Great. So we've got this string, and then we've got this function that allows us to set that string, is basically what's happening here. Here's the string getting set right here from the greeting that's passed in. So we deploy a contract with one transaction, and then someone makes another transaction that says, I'd like to update the greeting to this new string, and then the storage for the contract updates, right? Okay, so let's go play with it. Let's go see how it works. Let's interface with it. It's always much nicer when you can just have a front end. So what we'll do is we'll yarn deploy, and that's going to deploy our smart contract for free to our local blockchain where no one can see it. It's all localhost right now. We're just dinking around. We're learning how this works, right? And so the home page is really simple. It just looks like this right now, but the debug page is kind of the critical thing. We can see here is our greeting, right? It's telling us about our contract. It's telling us how much money is in our contract. It's telling us these global variables that are available in our contract, these storage locations, and then it gives us read functions and write functions. So what we could do is we could say, okay, let's update that string to hello world. Now this is going to fail. It's going to say, I don't have any money, right? You need money to make a transaction. So to make a transaction, we're going to need a wallet, and we're going to need money in that wallet. And Scaffold-ETH, now normally you would have some kind of like browser extension, and that's the thing that is your wallet. But in Scaffold-ETH, you need to be able to like quickly make transactions. So basically we take that private key that we've been talking about that you sign messages with, and it just lives in local storage. And so there is a burner wallet that's just built into my browser. And so I can just click, 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 and it's going to make transactions for me. This loaded me up. Now I have $11,000. Okay. So my account now has $11,000. And now if I say hello world, it's going to update my greeting. So this is a transaction. Each one of these clicks is a transaction. If I click, 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 I just made 3 transactions, and we can see the counter going up. So I just paid a little bit for each one of those transactions. And once this is a normal blockchain and the blocks are mined every, few seconds or 15 seconds, I have to kind of click, wait for the transaction to happen, and then come back. But on localhost, this is all instant, and we can kind of play around with things and make sure things work that's the way we want them to. Let's do something really interesting here. Let's copy our address, and let's require, so this greeting function, let's require that the message.sender is us. And we'll say not Austin. I'm Austin. Okay. So it has to be, we're requiring, this code is requiring that the person who comes into this function, the sender, that sent the transaction originally, it's kind of an interesting nomenclature there, but has to be this address. So I just took my address and I pasted it in, and I'm requiring that whoever calls that greeting has to be me. And if it's not, everything's going to revert. So if we redeploy this, the only person that can call this function now is this address, right? And we're going to test that in just a second. Let's make sure the happy case works. Let's say, hey, it's Austin, right? Okay, and I hit send. Very nice. Okay, Now, if we want a bad guy, I'm just going to create an incognito window. And I'm going to go to, what was that, localhost 3000. Okay. And it's going to generate me a new burner wallet. Notice this is kind of like blue and pink guy. This is kind of like yellow guy. Okay. So then let's grab some money and say, this is not Austin. This is a bad guy, right? Bad guy. Okay. And if the bad guy tries to set the string, he's going to get an error, not Austin, right? So that require statement threw him out of that function and didn't let him in. So that's how you kind of require that certain situations are set up the way you want for someone to do the rest of this execution. And by the way, it's all atomic. I can grab all of this stuff and I can put this require statement at the very bottom of this, and we can deploy that. And it's going to work exactly the same way. Basically, it's going to increment the counter. It's going to set the greeting. It's going to check this check. And then it's going to check this require statement and realize it's false. And it's going to roll everything back and undo everything, right? And so the ordering of this stuff gets a little bit tricky when we talk about that reentrancy bug I was talking about earlier, but technically everything is atomic. Now, if we were sending money in the middle of this, you want to do your checks and effects first before you do that send of money. But technically kind of this doesn't really make a big difference of where I put this require statement. It's just going to cost a little extra gas because it's going to execute through and then undo. And so you pay some extra gas to have that error, but it's all atomic. So if you get into this function and we send $5 to Alice and $10 to Bob, and then we hit a require statement that reverts, it's going to pull that money back from Alice and Bob. So what you can do is say, collect $5 from Alice, collect $5 from Bob, pay $10 into this new thing. And if anything reverts, give everyone their money back. And that's why that nice atomic nature of these transactions works that way. Okay, so you at home can grab Scaffold-ETH, you can pull it down, you can have this nice thing here where you can debug your contracts. Basically, let's go look at the docs real quick. And then when you want your front end to start talking to your smart contracts, you will write some hooks. And there's a lot of good documentation here. Let me paste it in. There's even me building an app in 8 minutes that you can watch here. But when you go to interact with your smart contracts from your front end, there's these two important hooks. There's use scaffold read and use scaffold write. And basically these read and write from your smart contract. Now, I'm not going to write any code. Let's YOLO a voting app, right? So I've got cursor up. Let me just undo all my changes. Let's go back to stock Scaffold-ETH here. Let's hit save. Okay. I'm going to go into cursor and I'm just going to prompt it to build that voting app that we had, right? This vibe check here. Let's build that on chain with a smart contract and a front end, right? So let's build a voting app that asks, how's the vibe? Answer is good or bad. Now's a good time to write a question in there if you have any questions. I'm just getting this prompt out there. There should be no owner of the contract, right? And no way to reset it. Every once in a while, it'll like add an owner and have a reset function. Reset the vote. We want users to be able to see the vote count and vote from the front page. Something like that, right? Boom, done. All right. So now we're going to use this agent, Claude, to, and within Cursor, the IDE, to plan out and write the smart contract and the front end. And Scaffold-ETH has a cursor rules here. It also has like, it's nice because there's a smart contract there and a front end there and everything's already wired up. So the AI is really good at pattern matching and figuring out like, oh, this is how I do that thing. Plus the cursor rules are there. So Scaffold-ETH is really good at kind of one-shotting these apps. Okay, we've got a question. One Ethereum block every 15 seconds with about 300 transactions seems like low bandwidth. That's absolutely right. Compared to a conventional transaction processing system. Yes. The bandwidth, what is the bandwidth? You're right. The bandwidth for the Ethereum network is way too constrained. And as soon as people start flooding that, you know, there's one lane. And as soon as that lane gets busy, it gets very expensive to use. I've deployed a smart contract before that cost me as much as my laptop. So you can end up having to pay a lot to use this network. When we're kind of saying this thing is always on, it kind of has that caveat of if a lot of people are using it, it's more expensive to use. So the throughput of Ethereum is limited, right? And the reason for this is security and decentralization. We want the EVM to be very simple. We want many, many very simple machines to be able to run this. So it's not going to do a lot of high processing. It is going to be bandwidth constrained. If you think about it like a settlement layer for other things. And this is where we get into Ethereum L2s. If I go to L2 beat, what an L2 is a layer 2. Basically, you take Ethereum, the network, and you make a copy of Ethereum, and you kind of have it settle to Ethereum. So there's all these little baby Ethereums, right? These L2s. Arbitrum Base, Optimism, Linea, ZK Sync, Lighter is a new one, Starknet, Unichain, Katana, Scroll, Bob. All of these are L2s. And basically, they're all baby Ethereums that take all of their processing and put them into these things called blobs and have them settle to Ethereum. And what that allows you to do is if everything on this network is down, if everyone is trying to steal your money, you can make a transaction on mainnet Ethereum on layer 1 and get your money out of the L2. Okay, so there is these security concerns that you can always have the uptime and the security of Ethereum by taking this L2 that runs a little baby Ethereum that's fast and cheap and has lots of throughput, and it settles to L1. So L1 Ethereum is probably going to be more like a global settlement layer and less like a thing that you settle every single transaction to, right? You'll probably deploy in a very important smart contract to L1, and then you'll have a whole bunch of stuff that runs on L2 and then settles to that L1 or something along those lines. And that's what we're seeing. If you go to Arbitrum and you go to make a transaction, it's going to cost a fraction of a cent. Just earlier, that payment that I was doing where I had a server that was a 402 server that did the vanity address creation and the client paid for it, that was on Base. And it was actually the facilitator that paid the gas, but it was still a fraction of a cent. The facilitator paid like 0.002 USD to make that transaction. So on these L2s, you get high bandwidth, you get low cost and high speeds. So you can deploy I could take this exact smart contract that I have on Ethereum and I can deploy it to Arbitrum or Base or Optimism. And it's going to cost me like 2 cents. It's going to cost me like a penny to deploy that smart contract. And it's going to cost you a fraction of a cent to interact with it. So there's these cheap, fast networks that are EVM compatible. And some of them, there's some like Arbitrum or Aztec that's going to be a different language. Some of them are all EVM compatible. Some of them aren't, and that's okay. They all settle to the L1 that is EVM compatible. So the throughput on Ethereum is limited, and the costs spike when you go to use it, and a lot of people are using it. But L2s are kind of the answer to that, kind of scaling horizontally, having lots of L2s. Okay, so here we go. Here is our vibe check. It deployed this. Let's go look at the smart contract real quick. We can see that, yep, it used that. Here's the contract. It's keeping track of, well, it does have an owner. I don't know why it has an owner. Vote good, vote bad, get votes, withdraw. Oh, okay. So for some reason, you can put money into the contract, and if you do, the owner can withdraw it. But other than that, the owner doesn't matter. I could even remove it, but we don't have time. Normally, I would prompt this and say, get rid of the owner. That's dumb. But really, someone can vote good. They can vote bad. It makes sure that you haven't voted before, and it keeps track of the bad votes and the good votes. So really nice contract here. Looks good and secure. The front end looks nice. Let's make sure we can vote good. Voted good happened. I don't know what that cannot access account was. Did that vote good happen? Yeah. Okay. Transaction happened. And then if I go incognito and we go localhost 3001 and we load up the bad guy, make sure the bad guy can vote bad. There we go. Great. Okay. You can vote good. You can vote bad. There's no censorship. You can't delete this thing. It's going to be up forever. Let's deploy this to Arbitrum. We're actually going to deploy this to a live network. Okay. So we have to generate an account. Okay, and I'm going to put in a password for that account. So basically, it's creating a private key. So then we have this address. I need to send that address some money real quick. Let's see if I can do that here. So we need to send to this address some Arbitrum ETH. Let's send it 0.0001. Yeah, 41 cents. That's more than we need. Send. Okay. And then we'll jump back over here and we'll yarn deploy Arbitrum again. Now that we've sent money to this account and we enter our terrible password. Here we go. We're deploying. There we go. There's the transaction. So we just deployed a smart contract live to Arbitrum and we paid real money. Now what we need to do is we need to go over here to the Scaffold-ETH config. And it's on hard hat. We need to tell it, nope, we're on Arbitrum now. We're deployed live. And if I hit save, my whole app is going to reload and it's going to be on Arbitrum now. So now we can connect. I can connect my wallet and I can spend real money, connect, and it's going to have me switch over to Arbitrum and I can spend real money to vote good. Okay. And this is a real transaction that's going to happen on the chain. And we can, let's see if we can verify our contract. I don't think we can. I feel like the Yarn verification is broken right now. There's a small bug in Scaffold-ETH we're fixing right now. So if we were to go look at this smart contract, it's still bytecode. And what you need to do is upload your code to the Block Explorer. They compile it, compare it to the bytecode. Oh, it's verified. Okay, here we go. So here's what it looks like when it's not verified. Okay, now if I hit reload, ta-da, there's our smart contract. And everybody can go read the code and they can see that it's connecting, counting votes all the same. The last thing we want to do is upload our front end. And let me just kill everything off and say yarn IPFS. So what this is going to do is upload our front end. So we've uploaded our smart contract and our smart contract exists on Arbitrum. And we can vote now on localhost, but it would be nice if we had a URL. If I can give you a live URL of the website and you can go to the website, you can connect your wallet and you can pay a fraction of a cent and you can vote good or bad vibes. You'll have to have some Arbitrum ETH, so it probably won't work here. But that's how you use Scaffold-ETH. You kind of use it locally. You deploy a smart, oh no. Let's see, we've got an issue. What I usually do is take this and throw it into the agent real quick and say, please fix, please go fix that. Yeah, I think we're done though. Sorry. Sorry if this ran over time. Go ahead. Sorry if there's any last, I'll try to finish deploying this and I'll paste the address to the chat, but I think that's the presentation. Definitely open for any questions or anything like that. Also, I'm Austin Griffith on Twitter and Telegram. If you want to just go find me here, I'm this guy. Let me paste it into the chat. DMs are open if you want to ask any questions. And I'm always around. Oh, it looks like our app is deploying. Thank you. Great questions. Go learn. Yep, go ahead, Agostino. Sorry.
Yeah, no, I'm thinking, Austin, I think this was extremely interesting. I mean, we have the video, so I mean, I'm sure that people will watch the again, or if they come up with questions after this session, can I send you an email or?
Yes, of course.
Okay,
they can even ask them in Twitter or Telegram. My Telegram is exactly the same as my Twitter, so I'm just Austin Griffith on Telegram.
Okay. Yeah, maybe you can. Yeah, I can put it on the chat or maybe.
That's in the chat. Yep.
Okay,
yep.
great. Yes.
Please reach out.
So feel free to reach
last
out.
thing, let's see. How do I go to?
Because some of them, Austin, are working on Agentics for smart contracts, so maybe they can ask you questions as the level of the project. Yeah.
Yes. Okay. And the app is live. I deployed it live now, and it's on IPFS, which is a interplanetary file system. So the app is actually stored in a peer-to-peer way. And let's see, we want to display a QR code. Sorry, we're running over time. There's the QR code. If you scan that, it will take you to the app that we just built, and you can vote on how the vibes are. And you'll pay a fraction of a cent. Yep. So go to ETH Build, learn some of these concepts, go to ethereum.org, go to Solidity by example. There's great, there's our curriculum, Speedrun Ethereum, speedrunethereum.com, but there's also Cyphren, there's Rare Skills. There's a lot of other good Ethereum education out there. And then the agentic stuff, go to that repo from Natter, go look up x402, go look up ERC8004. So many neat things happening kind of at the intersection of AI and blockchain. And my DMs are always open. Thank you for having me. Let's go see how the vote looks over here on our thing. Just my good vote. That's good. Okay, all
that's
good vibes then.
yeah. 100%. Yeah, exactly. Good. Yeah, I think it was extremely good, Austin. I think you managed to cover a lot of ground. Yeah,
For
well
sure. That
deserved.
was a
I
yeah.
like what you I like what your new background. Yeah.
Yeah, there we go.
Yeah.
Woo. Thank you
Yeah.
for having me.